So let's start with the second part of the chapter, the subspaces. Okay, and definition. Okay, for any vector space, okay, a subspace is a subset that is itself a vector space. Okay, under the inherited operations. Okay, so in the first part, in part 1, we have seen what a vector space is, and in this part we are going to talk about a subspace. So when you have a vector space and there is a subset in that vector space, and that subset itself is a vector space under the inherited operations, then that subset is called a subspace. I think the word itself explains it. So a sub of a space, okay, a subset of a vector space which is itself a vector space. Okay. So let me continue with some notes. Notes. Okay. Any vector space has a trivial subspace. Any vector space has a trivial subspace. That means subspace. That means the space made of zero. Okay. And as we have seen previously, a vector space must have at least one element. It's zero elements. Okay. Any vector space has itself for a subspace. Yeah. If any vector space has itself for a subspace. Number 3. So a subspace that is not the entire space is a proper subspace. Okay, so we say that a subspace that is not the entire space is called a proper subspace. It's called proper subspace. Okay, let me continue with the number 2. lemma. Okay. The lemma says that for any non-empty subspace S of V of a vector space, the following conditions are equivalent. For a non-empty subset S of a vector space under the inherited operations the following statements are equivalent. Number one, S is a subspace of that vector space. S is a subspace of that vector space. S is closed on the linear combinations of pairs of vectors. Okay, so S is closed on the linear combinations. That means addition and scalar multiplication. Okay, linear combinations of pairs of vectors. That means for any vectors S1 and S2 in S in big S. Okay. In big S. And for any scalars R1 and R2, element of the field R, the vectors. Okay, so near combination to me R1 S1, the plus or plus R2 S2 is in S. So basically, if you remember in part 1, for a set to be called a vector space, we need to verify the 10 conditions. But when it comes to the subspace, we can restrict those 10 conditions to only 2, which are vector additions and scalar multiplications. But we can even go one step further. The 2 conditions combine into only one, called linear combination. So as you can see here, the vector of S is being multiplied by scalar then this whole vector R1 S1 becomes a vector itself. The same the same thing for R2, scalar R2 multiplied by the vector S2. So this whole thing becomes a vector. So this becomes a vector on the left plus a vector on the right. You see, so that's called a linear combination. So that means if we have a subspace, it is equivalent of saying that that space, that subspace, or that set we call subspace, is closed under linear combinations. That means it's closed under addition and under scalar multiplication. Okay. And number 3, third condition says that S is closed on the linear combinations of any number of vectors, not only on the 2 vectors, but on the any number of vectors. So S is closed on the linear of any of vectors. For any vector or vectors S1, S2, Sn in the subspace S, and for scalars R1, R2, Rn in R, the vectors, okay, the vectors R1, S1, this is data, plus R2, S2, plus dot 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 R, N, Sn is an element of S, so is in S. Or briefly speaking, a subset is a vector space if and only if it is closed under linear combinations. Okay, so that is our lemma. So in order, if we have a space and then we have a subset of that space, to prove that that set of the space is a subspace, we need to prove only closure on the linear combinations. Okay, so I will stop the lecture here, and in the next video I will do a tutorial. I think I have few questions. We will do few questions in that tutorials to prove when a subset is a subspace. Thank you. See you.